in the emitter bias, you know that emitter terminal is connected in series with emitter resistor, RE, right? And the collector terminal is connected to RC, you know that. And the base terminal, okay, so this is your base, is connected to RB. So in this case, what I will do, instead of RB, let me rename that resistance as R1, okay? And the junction gets connected to the power supply voltage VCC, right? So this is your emitter bias, okay? Now, how do we achieve voltage division? So in order to achieve voltage division, what you have to do is you have to connect an additional resistor between, okay, I'll use a different color so that you'll be able to distinguish. So what I'll do, I'll connect a different resistor between base and the ground terminal. And that resistor, I'll call it as R2. So this is your voltage divider bias circuit. You see, very simple to remember. You don't have to bucket anything. Just trust on your logical aptitude. All right, fine. So that's your equivalent circuit. Now let me draw the equivalent circuit. Okay, equivalent circuit is pretty simple to draw. First, let me draw the transistor symbol. Okay, I mark the respective terminals: base, collector, and emitter. Okay, emitter is connected in series with the emitter resistor RE. Okay, and if you observe carefully, see here, the base terminal is connected to one end of R2 and the other end of R2 is grounded. Okay, so let's connect the base terminal to one end of R2. Okay, and the other end of R2, okay, I have marked the X terminal, is grounded. So what we can do, you can bring that other terminal and you can directly connect it to ground. All right, so that's how we connect R2. Let's look at the connection of R1. So one end of R1, say the dotted terminal, is directly connected to base, right? So let's connect R1 to base. So that's your node, okay? Say this itself is your base terminal. That doesn't matter. Okay, so that's your R1. And the opposite terminal of R1, say X terminal, is connected to what? Positive terminal of battery. Directly you connect it to plus terminal of battery. And you know that the negative terminal of battery will be held at ground potential in case of NPN connection. Okay, and that's your VCC. Okay, so this is your input circuit. Let's do the same thing on the output circuit. So collector terminal is connected to RC, right? So just connect your collector terminal to RC, and the free end terminal of RC is connected to VCC. So that's the positive terminal of VCC. So bring it and connect it to plus VCC. All right, and the negative terminal of VCC is connected to ground. Okay, fine. So that is your equivalent circuit. Okay, so this is your circuit, and B is your, in short, let me write, equivalent circuit. Okay, now comes the analysis part. Okay, so output circuit analysis, you don't have any problem, because on the output circuit, you can directly apply the KVL, because you don't have loops within, right? You will have only one output loop, hence you can easily apply KVL. Okay, let's mark current also. Okay, so this is your IE, hence there will be a drop across resistor RE, which is IE into RE, and this is the flow of collector current, let's say IC. Okay, and this is your IB. Okay, now here you have a base terminal, right? And to this base terminal, two resistors have been connected. So basically what happens is that the current which flows through R1 and R2 are different. So what we can do, let's take this current as I1, okay? And current through R2, let's consider it as I2, okay? Fine, so that's your equivalent circuit. Now, if you look at the equivalent circuit closely, You can say that the output circuit is similar to emitter bias circuit. Okay, and it is also similar to your collector to base bias circuit. But the input circuit is different. Okay, in the previous three circuits, you used to get a single loop on the input circuit. Okay, but over here you have a double loop. You have loop 1 as well as you have loop 2. Okay, now how do we write KVL equations for the input loop? Okay, you may argue that we can go for mesh analysis or nodal analysis, but trust me, mesh and nodal analysis becomes very complicated. It gives very complicated equations. That's because in case of transistors, on the input side, you don't have one single current. You basically have 4 currents. If you look at closely on the input side, you have current I1, you have current I2, you have base current IB, and you have emitter current IA. Okay, so when you deal with 4 different currents, the equations what you are going to get using, say, mesh analysis is going to be a very difficult equation to handle. Okay, you are going to get a kind of crazy equation. So that's the reason we don't go for mesh analysis. Okay, instead we go for something known as network theorem. Okay, network theorem. Okay, so you have several network theorems. Out of those many network theorems, what we are going to choose is a theorem called Thevenin's theorem. Thevenin's theorem. Okay, so this Thevenin's theorem basically makes our life simple in the sense, whenever we have a complicated network consisting of many voltage sources and many resistors, okay, by applying Thevenin's theorem to the complicated network, you can construct a very simple network consisting of only 2 elements, Thevenin's voltage source and Thevenin's resistance. Okay, so the crux of Thevenin's theorem, I can put it in a diagrammatic manner. Okay, let's say this is your complicated network. This is your complicated network consisting of several VXs, that is voltage sources, several current IXs, and several resistors RXs. Okay, so this is your complicated network. So using Thevenin's theorem, okay, so what you do, apply Thevenin's theorem. Okay, apply Thevenin's theorem and convert that complicated network into a very simple network consisting of only 2 elements, VTH called as Thevenin's source, voltage source, in series with RTH called as Thevenin's resistance. Okay, Thevenin's resistance. So this is what we are trying to do. Okay, so on the input side, in the end, you are going to see only 2 elements, VTH and RTH. How to calculate VTH and RTH? That is what I am going to teach you now. Okay, so you can write since BE loop is complicated to deal with Thevenin's theorem is used to solve the network. Okay, I hope you have understood the Thevenin's theorem usage. Okay, complicated network can be converted into a simple network consisting of only 2 elements, Thevenin's voltage source VTH in series with Thevenin's resistance RTH. Okay, since BE loop is complicated to deal with, Thevenin's theorem is used to solve the network. Okay, fine. Now, to apply Thevenin's theorem, the following steps are applied. Okay, to apply Thevenin's theorem, the following steps are followed. Okay, first you have to identify the load terminal. First, identify the load terminals. Okay, can someone tell me what is the load terminal? Load terminal is nothing but the output terminal. In our circuit, what are the output terminals? The output terminals are collector to emitter terminal. right? So collector to emitter terminal. So what I will do, I will just draw the shade, okay? So you can say that this entire transistor, the highlighted part, okay, the highlighted part can be considered as the load, okay, can be considered as the load, okay. So what I will do, I will just write load. So my output circuit is basically load. So what I will do, I will cut my circuit diagram somewhere over here. Okay, I will bisect my circuit somewhere here. Okay, and that is I'm going to. I mean that is what the load meaning is all about. Okay, so I will remove off the load terminal. So what I will do here, I will write remove the transistor symbol. Okay, just remove the transistor symbol. So what happens? Entire right hand side gets vanished. Okay, next step, find VTH. Okay, and third step, find RTH. Okay, 3 steps. First step, identify the load terminals and remove them. So transistor is basically a load for us because the transistor's collector to emitter terminal is considered as the load terminals, right? Because that belongs to the output part of the circuit. So that you remove it off. Okay, and then you go for step 2, that is finding VThevenin. So VThevenin is found, okay, by measuring open circuit voltage across the load terminal. Okay, so VTH is equal to open circuit voltage measured across the load terminal. So where you get this open circuit? You get the open circuit from step 1. In step 1, you will remove the load terminals, right? The moment when you remove the load terminals, you will get an open circuit across the output circuit. So measure the voltage across the output circuit. So that will give you the Thevenin's voltage VTH. Okay. So once VTH is found, you can proceed with RTH. Okay. Let me tell you how to find RTH. To find RTH, what you do is short circuit voltage sources and open circuit current sources. Okay, if at all you have any current sources, you open circuit, and then you measure the equivalent resistance across the load terminal. Okay, that's all. So this is how we saw Thevenin's problem, which holds good for network analysis as well. Okay, so basically I'm pulling the concept of network analysis into analog electronic circuits in order to keep my analysis simple. All right, don't worry, I'll tell you how exactly you find RTH, VTH, etc., etc. Fine. So first let us apply step 1. Okay, what is that you're supposed to do in step 1? In step 1, you're supposed to remove off the load. Okay, so I'll just write the subheading. In step 1, let me write the objective. Okay, so objective is to remove the load. Okay, that means to say remove the transistor. Okay, fine, let's do that. So this is your base terminal, so emitter terminal, and this collector terminal. Okay, so what we will do, we will isolate the transistor. Okay, isolate the transistor in the sense, okay, this part we need to remove. I'll remove it after some time. Okay, before that, let me connect a few of the things. R2, right, and then R1, and then this is your ground terminal. VCC plus minus. Okay, fine. So this is where you will be having your emitter resistor, right? So this is my equivalent circuit for step 1. So remove the load we are claiming, right? That means to say remove the transistor. So let's remove the transistor and let's see what exactly we get. So removing the load is nothing but doing this activity. All right. So this is what the circuit looks like now in step 1. Okay, fine. Step 2. So you can say that load is removed. Okay, step 2. Okay, what is step 2? Find VTH. Okay, to find VTH, what we do is, okay, this I will write circuit 1. Okay, find VTH. To find VTH, what you have to do is use circuit 1 and measure the voltage across the open circuit, terminals. Okay, so let me open circuit terminals. Okay, so this is your open circuit. So here what we are supposed to measure the voltage. Fine. VCC, R1, R2. This is R1, this is R2, and this is VTH. This is VTH, minus, plus. Okay. So what is VTH? Can anyone tell me? VTH is equal to, can I say, voltage across R2? Correct, no? VTH, the open circuit voltage, is nothing but voltage across R2. Yes or no? Can anyone confirm? Can you confirm? Therefore, VTH can be given as voltage across R2 is nothing but current through R2 into resistance R2, right? So it is I into R2. Okay, since there is only single loop, we can take that current as I. So VTH is equal to I into R2. So what is I? Which is equal to, what is I? I is equal to voltage divided by total resistance, R1 plus R2. Okay, voltage divided by sum of the resistance, Ohm's law I'm applying, into R2. Okay, or in other words, we can say the voltage source VTH or the Vennens voltage source VTH is equal to source voltage into R2 divided by R1 plus R2. Okay, so basically this expression follows voltage divider rule. Okay, voltage divider rule. Okay. So that's your VTH. So on the input side, you can simply represent a voltage source. Okay, and what is the source representation is given by? The source representation is given by the product VCC into R2 divided by R1 plus R2. Okay. Did you understand? Any hiccups till now? Any problems? Can you confirm? Do you have any problems in understanding the Vennens theorem? No? All good?
Yes, sir.
Okay. All right. So we have found VTH. Now let's find RTH. Okay, which is called as Thevenin's resistance. Thevenin resistance. Okay, how to find Thevenin's resistance? In step 3, probably I have mentioned. Yeah. To find Thevenin's resistance, what you have to do is, if there are any voltage sources, you short circuit them. And if there are any current sources, you open circuit them. Okay. And then you measure the resistance across the load terminals. Okay. So our circuit is consisting of how many current sources? Can quickly tell me? Our circuit is consisting of how many current sources? Unmute and tell me, no problem. Look at the circuit diagram and tell me, are there any current sources in our circuit diagram?
No current source.
No current sources. Only one voltage source we have, right? So you don't have to worry about the current sources. Only one voltage source you have, that is VCC. So what we can do is short circuit VCC. Okay, so I will short circuit VCC. Okay, here let me write VCC is shorted. Okay, and then rest of the circuitry kept the same. Okay, so that's R1 and that's R2. Okay, and this is your base and this is your ground terminal, right? Ground terminal. Okay, and this is where you are supposed to measure RTH. Okay, it's something like you are connecting an ohm meter. Okay, ohm meter is nothing but resistance measurement instrument. Okay, ohm meter across base and ground terminal. So what is RTH? Can you quickly tell me? Can anyone tell me what is RTH? What do you see when you look at the circuit? When you see the circuit, okay, from the output side, you see that the two resistors are connected in some manner. Okay, so you can see that, say, dotted terminals are connected together at one end, and let's say the triangular terminals are connected together at some other node. So this is something like two resistors are connected in parallel, correct? Dotted terminals are connected together somewhere here, and the triangular terminals are connected somewhere here. So nothing but, you have a parallel combination of R1 and R2. So RTH is basically R1 parallel with R2. That's R1 into R2 divided by R1 plus R2. Fine. So that's our Vennens theorem. So you have found VTH and you have found RTH. Okay. So in the last step, which I haven't mentioned, okay, step 4, you can mention that connect the load with the Thevenin's circuit. Thevenin's circuit. You had removed the load, right, in step 1. Now you are supposed to place it back, okay, because you have reduced the input circuit. So the final circuit looks like this. Okay, you will not have VCC, okay, because you have replaced VCC with VTH, and you will not have, what do you say, R1 and R2, because R1 and R2 have been replaced with RTH. Okay, and that's your base terminal. Okay, so, and this is your ground terminal. This is your ground terminal, say G. Okay, so now insert the load. Okay, this is your base, right? So insert the load. Let me insert the load now. This is RE. That's collector, to which collector resistor RC is connected, and then connect VCC. Okay, so that's your Thevenin's circuit. I mean, the complete voltage divider bias circuit. Complete voltage divider bias, VDB circuit. Okay, can you quickly tell me, this circuit takes the shape of what biasing network? This circuit is equivalent to dash biasing network. Quickly.
Emitter.
Emitter bias. Yeah, only the difference is VCC for emitter bias, and in place of RTH, you have had RB for emitter bias, right? Rest all remains the same. So the analysis will also be the same. Okay, so quickly we can take up the analysis. Okay, so this is your VBE plus minus. Okay, this is your VCE, upper side positive, lower side negative. Okay, now you can apply the KVL. Let us mark currents. This is IA, IB, all right, and this is IC, okay, and let me apply KVL in clockwise direction for the input circuit and anti-clockwise direction in the output circuit. So apply KVL to the base emitter loop. Okay, it gives VTH minus IB into RTH minus VBE minus IA into RE is equal to 0. So you can replace IE with 1 plus beta times IB. So you get VTH minus IB into RTH minus VBE minus 1 plus IB times, sorry, 1 plus beta times IB into RE is equal to 0, or rearrange the equation to get an expression for IB. So IB is equal to VTH minus VBE divided by RTH plus 1 plus beta times RE. Okay, so as expected, the expression is similar to an emitter bias circuit, with the exception that VCC is being replaced with VTH and RB is being replaced with RTH. Okay, all right, so that's your equation 1, which represents the base current equation, and the collector current equation can be written as beta times IB, the transistor equation. That is equation 2. Okay. Now apply KVL on the output circuit. Okay, what is your output circuit? Common emitter loop. All right, so when you apply KVL on the output circuit, okay, in anti-clockwise direction, I think I don't have to mention because that's how that is how I have been applying KVL in the past also. So it's VCC. Remember, do not get deceived. On the output circuit, we don't have VTH. Okay, only on the input circuit we have VTH. On the output circuit, we still have VCC. Okay, so it is VCC minus drop across RC minus terminal voltage minus drop across RE is equal to 0. And on the output circuit, you can write IC is approximately equal to IE. So VCC minus ICRC minus VCE minus IC into RE is equal to 0. Or you rearrange the equation to get the terminal voltage, the output terminal voltage VCE, which is nothing but power supply voltage minus different resistance drops. So IC times RC plus RE. So that's your equation 3. Okay. So equation 3 basically represents the transistor output voltage VCE. Okay. So having found equation 3, I think you can proceed with the load line construction. Load line analysis. So load line analysis helps you in understanding the Q point location on the transistor output characteristics. All right, so fine. So let's quickly draw the load line analysis. First, let me draw the axis. Okay, y-axis, x-axis. Okay, and mark the axis. Output current IC in milliamperes, output voltage VCE in volts. Okay, and when IC is equal to 0 in equation 3, so that means to say when we put current is equal to 0 in equation 3, we get VCE is equal to VCC. Okay, which is nothing but VCE saturation, the maximum voltage, the maximum possible output voltage, which is equal to the power supply voltage. On the other hand, when we put VCE is equal to 0, you get IC is equal to IC saturation, okay, which represents the maximum collector current, which is nothing but the ratio of VCC divided by RC plus RE. Okay, so this is your x-intercept and the later being your y-intercept. So that's your y-intercept. And what's the value? IC saturation. And this is your x-intercept. And what is the value? VCE saturation. So basically, IC saturation and VCE saturation sets the limit for your load line. So in between these 2 points, you are supposed to draw the straight line. So that represents your load line. Okay. So this is your load line. And the slope is minus 1 by RC plus RE. Okay, so that concludes the analysis of voltage divider bias circuit and the completion of the biasing circuit analysis.